to a constant, like Lie heights usually are, you can hope there are some nice formulas to go around. And so there's a beautiful conjecture due to Kolmez, which says the following thing. Let's suppose A has CM type K phi, and the endomorphisms of A are the full ring of integers. He actually insists on this in this case. I presume you can get a formula in any way, but in any case, but his formula, his conjecture is written down, has this condition inside it. Then the Faltings height of A is equal to the following thing. You take a sum over irreducible representations rho from the Galois group of the normal closure of K over Q to some GONC. You sum over all irreducible Artin representations. And now you have some rational constants, 0 phi, which depend only on the combinatorial data involved, not on the actual field, just somehow the group G together with combinatorial data of phi, multiplied by the logarithmic derivative of the L function at 1 plus the log because K might not be Galois, so I'm just thinking, just the normal closure. That's right. Okay, so we're not really relevant to us, but these are numbers that are rational and somehow only depend on combinatorial data. Okay, so this is a beautiful conjecture, and let me write down a sort of immediate corollary of it once you know what modern analytic number theory already knows. And the corollary is that if you look at the Faltings height of this abelian variety, I'll write it in absolute value, but in fact Faltings height can't get too small, then this grows subpolynomially in the discriminant. So it's kind of funny. It's a very beautiful and precise formula, and we're only going to use it in this very sort of perverse, lighthearted way. But without this formula, I'm hard-pressed to give you any bound whatsoever on this Faltings height. So I used to say that I in fact, can't give any bound on it. In fact, I've thought about it. You can probably give some exponential bound in discriminant if you work really hard. But if you want to give a reasonable bound for this quantity, I really can't see how to do it without using some precise statement like this. So it's kind of a funny situation, I think. So let me give the proof. I'll give it inside of this box. Okay, so because these guys only depend on combinatorics, there's finitely many possibilities of them. So if I just show you that all of these terms are small, then that'll show that their sum is small as well. And the proof is the following. So let's see. Well, the Artin conductor is bounded by some power of the discriminant of K. And log grows subpolynomially. So that's this term here. Proof. We need to bound this from above and this from below. So L of 1 rho, this is actually the most subtle term in this expression, in absolute value, bounded below by the discriminant to the little of 1. So I'm going to get it wrong again. I think it's just Siegel who did this, right? Or is this Brouwer now? Okay. Brouwer Siegel. That's somehow what their main theorem about class groups amounts to, is this lower bound. So it's deep. It's been known for a while, but it is somewhat deep. Right. Absolutely. Mm-hmm. There are certainly several cases you can prove effectively from Stark's theorem, from Stark's work. Oh, I see. Right. Right. Oh, I see. Okay. And so finally you get a bound L1 prime rho, and this is true, that this guy small is true by the standard convexity bound. This way, the standard convexity bound tells you that L is small near the 1 line, and then if you combine it with Cauchy's integral formula, you get it for the derivative as well. Pardon me? Yes. So, yes. Yes, everywhere here G is fixed, absolutely. Throughout everything I do. Yeah, if you start varying the degree of the number field, it's a whole different ball game which I know nothing about. So G is always fixed. Okay, but you put these three facts together and you get immediately from Colmez. And somehow some known but deep work. All right, so Colmez is not known, and it doesn't seem like it's very close to being known. But there's somehow an average version of it which is known that turns out to be sufficient, which is why we can still end up proving the theorem. But I want to save that to the end, and right now let me just show how Colmez would imply the André-Oort conjecture. I want to give you a brief sketch of somehow the ideas behind the proof. So theorem, the Colmez conjecture implies André-Oort. Well, let me say it implies conjecture 1G. That's what I'm really going to prove. Okay? So I want to explain how that goes. So it's going to be a few ingredients. One ingredient is going to be this corollary here. Another somehow massive ingredient we're going to use is the theorem of Masser and Wuttholz. And the version I'm going to use, I think, was proven in '96, though they had worked on it for several years, and refinements of it. And this is going to be a huge powerhouse theorem. They proved it to give a different proof than Faltings of the Mordell conjecture. Of part of the one. Really? Oh, part of. Okay. Part of the Mordell conjecture. Okay. And it says the following. So suppose that A and B. So once again, let's fix G. Always fixed. And suppose A and B are abelian varieties over some number field K of dimension G. And say that somehow I know that they're isogynous. So I know there exists some magical isogeny between them. So then it turns out that there is in fact an isogeny between them that's not too big. It has a degree that's not very big. So then if you let n be the minimal degree of an isogeny between A and B, then n is bounded above by the maximum of the Faltings height of A, or I could put B here also, and the degree of the field K over Q to the power of some constant, let me call it C sub G, depending only on G. Okay. So if I give you two abelian varieties that are not arithmetically complex, defined over some low degree number field, and you know that they're isogynous, there's in fact a low degree isogeny between them. All right? Okay, and it turns out that these two are sufficient to prove conjecture 1G. So let me now give you the proof. of 1G from these two guys. And we'll do it as follows. So define a set S to be the set of all abelian varieties A, such that A is principally polarized, the endomorphism ring of A is the full ring of integers of K, and A has CM type K, comma, some phi. Okay? So look at all such abelian varieties. Now, in the case of elliptic curves, these form a single Galois orbit. In general, that's very much not true. They can split up into lots of Galois orbits. And even though the size of the Galois orbits we're trying to get at, and that's kind of subtle, the size of S is actually pretty straightforward. So this is up to constants. Let me put it in quotes. I'm not quite sure what the constants are. But the size of this is the size of the class group of K divided by the size of the class group of the totally real subfield of K. And again, using Brouwer-Siegel, that happens everywhere, this is at least of size discriminant to the 1/4. Okay, so regardless of what's what, if you give me a CM type, then I can give you lots of abelian varieties that are principally polarized of that CM type. So they exist without much fuss. Okay?